Okay, good morning. Welcome back. It's great to see everybody. I missed last week, but I heard it was. I heard all about it. It was so. They're good, aren't they? Yeah. Wait till you hear Jeremy. Yeah. So first week we covered sort of the plan, and last week and this week are about what we're doing now. Of course, last week the theme was sort of the astronauts home away from home. How are we going to keep them alive as we go into deep space? This morning you're going to hear about how do we get out into deep space. And in particular, how do you get out of this gravity well that we live in? We live at the bottom of a really deep and steep gravity well. And so if you want to get off the Earth, it takes a lot of energy to climb out. And so Jeremy Pinier is here this morning. He is the technical lead at Langley for all the work that we're doing at Langley in order to make the next generation rocket fly. And it's a lot of work. There's as you can imagine, when you get that much energy into one place and try to fly it through the atmosphere, a lot of fun things start to happen. And he's in the middle of trying to figure out how to make it safe and how to make it stable as it goes up out of the atmosphere. Next week, of course, we're going to start to talk about the problems that we haven't actually figured out how to solve. We think we know how to solve this rocket problem. It's a lot of work. We think we know how to solve the spacecraft problem. And again, it's a lot of work. It's taken us some time, but we have the solutions. For the next two lectures after today, we're going to be talking about things that we're still working on the solutions for, frankly. And so, in any case, that sort of sets the stage for next week. But at this time now, I'm going to turn it over to Jeremy and let him tell you about the SLS and Langley's role in that.
All right. Thanks, Steve. Thanks a lot. Can you guys hear me in the back? Yep. Pretty well? All right, thanks. So again, I'm Jeremy Pinier, and I work at NASA Langley Research Center about 8 miles from here. And we're going to talk today about rockets. So this should be fun. And in particular, we're going to talk about the Space Launch System that you see right there. That's our nation's future heavy lift launch vehicle to carry humans back to Mars, or back to the moon and even further to Mars. So I really have my dream job. I'm not going to lie, I love my job, but nothing that we do at NASA could be done by any single person. It takes teams, very large teams of amazing people to do what we do. And I have to give credit to the wonderful people I work with. These are some of the team pictures that we take when we're running wind tunnel tests. We're going to talk more about that. And our team is not just here at Langley. It's in Alabama at the other NASA centers. It's in Houston. It's in California. And we all work together to make this rocket work. So, first of all, I'm going to give you right off the bat 4 takeaways for today. I'm going to show a lot of pictures. I'm only going to show 4 equations, and if you don't understand them, that's just fine. We can't talk about rockets and not have equations. So, but I want you to have 4 takeaways, and the first one is going to space is really hard. Just like Steve mentioned, we are fighting 2 very strong forces. One of them is gravity, the other one is drag when we're shooting out of the atmosphere, and that is hard to do. The second takeaway is exploring space benefits our society as a whole. We're not just exploring to discover new worlds. I mean, we do it because that's amazing and fantastic, but we also do it because of all the benefits and the spin-offs that we get in our society here on Earth. The technology that's developed to go to space, we have to push the envelope of knowledge, and all of that benefits all of us here. So that's really important. The third one is today is really an exciting time for exploration. Humans haven't really explored for 40 years. Last time humans explored was when we were going to the moon. Obviously, we've done fantastic things like the space station and developed new technologies, but now, today, we're developing a new rocket to do some more exploration, even further than we've ever been. And fourth of all, oh, did I mention that going to space is really hard? Well, that's another takeaway here, and we'll see why it is. So, as an outline, 4 things. Actually, it looks like 2 number 1s, a number 2, and a 3. So, Mac PC issues here. First of all, I'm going to give a brief history of spaceflight. So we're going to talk about how do we get out of the atmosphere, and I'm going to give a very brief history of how spaceflight is what it is today. Second, I'm going to talk about the Space Launch System, SLS. I'm going to say that word many times, SLS. So hopefully you'll remember it and you can talk to your neighbors about SLS when you get back home. That's America's next rocket for deep space exploration. Third, we'll see what NASA Langley is doing here in our backyard to contribute to the Space Launch System. And fourth, we'll go first full circle back to some history about how Hampton Roads is really the manned spaceflight of the birthplace of U.S. manned spaceflight. And that's pretty amazing that happened right here in our backyard. So, like I said, going to space and escaping Earth's gravity field requires piercing through our atmosphere at great speeds. That's a beautiful picture of our atmosphere taken from the space station. You can see how fragile it looks and beautiful, yet it is so hard to pierce through it because we're going so fast. And here's equation number 1. All you have to worry about is the circled term there, that's velocity. That's how fast we have to go, or that's how drag, the force of the air on the rocket, that's how drag is proportional to velocity. So that's the square of velocity. That means that if I'm going 50 miles per hour on the highway, I stick my hand out the window, and I'm going to get a force of maybe 30 pounds on my hand. If I go twice the velocity, if I accelerate to 100 miles per hour, which we shouldn't do, that's a little fast, but let's just a thought experiment. My hand is now going to see a force that is not double, it's quadruple. So it's 120 pounds. So that's one of the issues. The other issue is that if you look at the power requirement, equation number 2, the power requirement to overcome drag is proportional to the cube of velocity. That means that your car, when you doubled your speed on the highway, you now have to use 8 times the power. So that's why your gas mileage goes down really fast when you start going to the speed limit compared to like 40 miles per hour. So that's the really hard part. And that nature gave that to us. That's an equation given to us by nature. There's nothing we can do about it. Okay, so we know we have to go fast, but how fast do we have to go? All right? Well, it depends on where we want to go. That's the whole issue. We can go close to the Earth, or we can go really far, and that's going to determine how fast you need to go. This is equation number 3, and that's the escape velocity that is needed to go to a certain point. So the capital M, that's the Earth mass, okay? And little r, that's the radius of the Earth. So that determines your escape velocity. So we calculate that very easily. So if we want to go to Mars, which is what we're going to try to do by the 2030s, that is the velocity that we need to obtain to get there, 25,000 miles per hour. There's no way around it. If we want to go to another solar system, so if we want to escape the sun's gravity now, that's 95,000 miles per hour. And that's been done before. I'll show you the first spacecraft that did that. Yeah?
Wouldn't it be
Yeah. It is. This is just assuming, let's try to go straight there, just to simplify things a little bit, but yeah.
That's my question too. All of those assume we're starting from the Earth.
Yeah, you're absolutely right. Yeah, I'm simplifying things, and this is just so you get the concept of escape velocity. And we would do that if we had to go. International Space Station, 18,000 miles per hour. And for space station, we have to go directly. There's no exactly, no stop along the way. And for the moon, that's about the escape velocity to get to Mars. It's pretty similar. Once you're on the moon, escaping the Earth's gravity is not that hard. So, all right, this is not to scale. So I think scale is important because I've described how fast we need to go. Now, how far do we need to go? So to explain how far we need to go, I brought this globe, and let's just imagine that it's 3 feet wide instead of 1 foot wide. I couldn't find a 3 foot wide globe. But this is planet Earth, okay? If this is Earth, the size of Earth, the sun would be 6 miles down the road, about at Newport News Park over there. And it would be 333 feet wide. That's the size of the sun compared to this globe here. Mars, and obviously the Earth is going around an orbit, 6-mile orbit around the sun. Mars is 3 miles that way, okay? That's where we're going to try to go. Now, the moon would be about at the end of this room down there, it'd be about 3 yards, about 9 feet wide. No, I'm sorry. It's about a third of the size of Earth. Okay, so the moon's over there. Mars is 3 miles down the road. International Space Station, it's an inch away. Okay, that's where we've been going for the past taking humans for the past 15 years is an inch away from Earth, and that's what we call low Earth orbit. Okay, that's we have vehicles today that can go to low Earth orbit an inch away from the Earth. We don't have a vehicle yet to go 3 miles down the road. And that's what we're going to talk about, is the Space Launch System, this big rocket that's going to take us there. Here are some of the first man-made objects that attained these velocities, these very high velocities. Sputnik in 1957, you all know about Sputnik. That was the first satellite to get into low Earth orbit, right, an inch away from the Earth. Luna 1, that was the first spacecraft to escape Earth orbit. It ended up in orbit around the sun, but that was by accident. They were the saying, shoot for the moon, and if you don't, you can always hit the stars. That's exactly what happened. They were shooting for the moon and missed it. There was an issue. It's complicated, right? It's hard. And this is a long time ago. They missed the moon, and now this satellite is still in orbit around the sun somewhere in between Earth and Mars.
That's Soviet Union, right?
Yeah, both of those, sorry, yeah. Both of those are Soviet Union. And then we have a first from the U.S., that's Voyager 1, 1977, first to escape solar orbit. That spacecraft just recently made the news because it is now past, it's now outside of the solar system. It took 37 years to get there at that velocity. So that gives you an idea of the size of the solar system. So that's a tremendous feat. Now, many people have contributed to spaceflight, but I'm only going to talk about 3 because we only have 1 hour. So these are 3 giants, really, that we all stand on their shoulders as far as our knowledge and where we are today. This is Konstantin Tsiolkovsky, born in 1857, died in 1935, a Russian. He is considered the father of spaceflight. He conceptualized all kinds of technologies that we're now still only developing. Back in the beginning of the 20th century, he was probably 30, 40 years ahead of his time. People didn't understand what he was talking about, but he published around 400 articles. 90 of those are related to spaceflight. And one of those is the exploration of cosmic space by means of reaction devices in 1903. He developed in that article much of the theory behind space travel and rocket propulsion. So he was a theoretician, right? He didn't develop any rockets. He didn't build them, launch them, or anything. He just thought, in his head that we could do that. He came up with multi-stage rockets, space stations, and all kinds of concepts that we're now all familiar with. But back then was just imagination. And this is one of his drafts of what a spacecraft looks like. You've heard about Orion spacecraft, probably. That's today's spacecraft. We've come a long ways, as you can see. but he already had a lot of ideas on what a spacecraft should look like.
And he was Russian.
He was Russian, that's right.
It's like Leonardo was for aeronautics.
It is, absolutely. That's a great comparison. And he came up with our last equation for today, the rocket equation. Can't go without that rocket equation. And it relates what speed you need to what mass of fuel you need in your rocket, depending on how efficient your rocket is, to that velocity that you need to get. So it's an equation that everyone uses today, of course. The second person that I'd like to talk about is Robert Goddard. You may know about him. He's an American, lived in Massachusetts his whole life, 1882 to 1945. He took that theory that Tsiolkovsky came up with and made it happen. All right, so this is a picture from 1926. This is the first liquid-fueled rocket in the world in 1926, and that's Robert Goddard standing there. He had a team of a lot of people that helped him, but he was an engineer, physicist, an amazing person. And so let's think about this. This is 1926. Neil Armstrong was born in 1930. That's 4 years after that picture was taken. And he ended up flying on Saturn V and walking on the moon. So that's how fast we evolved with spacecraft. It's amazing. The third person is Wernher von Braun, 1912 to 1977, came from Germany after the war, and without Dr. von Braun, we would have probably not been to the moon that fast. He had developed technologies with his large team of engineers that enabled us to really get to the moon as fast as we got there in that decade. He played a crucial role in early development of large rockets and missiles and was really instrumental in scaling up the designs to allow for travel. He ended up being the director of the NASA Marshall Space Flight Center, but was really an engineer, and he was involved deeply in the development of these rockets. That gives you an idea of the scale of the Saturn V rocket. Those are the main engines. There's 5 of them on the Saturn V. And I mean, it's just humongous. And thanks to all the people that worked on the Apollo program, Saturn V and Apollo program, we had 13 successful Saturn V launches. And you might say, well, Apollo 13, was that successful? Well, maybe it wasn't a completely successful mission, but it was a successful launch. The launch of the rocket was successful. So 13 successful flights, 6 lunar landings. We didn't go to the moon just once. We went 6 times, Apollo 11, 12, 14, 15, 16, 17. Landed 24 humans on the moon. More recently, since that time, we've developed, or the world has developed, multiple rockets that you've heard about. This is the Soyuz, the Russian rocket that we're still using today to get to space station. Space shuttle, obviously, without space shuttle, we wouldn't have a space station today. We've got a Delta IV Heavy. That's a Boeing rocket, U.S. rocket. Atlas V, that's a U.S. rocket as well. Sea Launch, that's a rocket that launches from anywhere on the ocean, so it can launch from an optimal location. We've got Ariane 5, that's the European rocket that's currently in use. And then we have these two rockets that are really the first commercially funded or commercially developed rockets. It is on the right, that's the SpaceX Falcon rocket, and then that's the Orbital Sciences Antares rocket. Both of those were developed by private companies, and they've been doing an amazing job to get to low Earth orbit. So, and then I can't give a history of spaceflight without showing a picture of the space station. It's a marvel of technology. It's the size of a football field, and it took many space shuttle flights and a huge amount of effort to do that. But we're now doing some amazing science on the space station, learning a lot about health, about physics, chemistry, and all kinds of radiation and things that we're going to need to know more about if we want to go to Mars. So here's where it gets exciting for today is the next frontier for human exploration is Mars, an asteroid, or some type of equilibrium point in the Earth-Moon system. You might have heard about those. Any one of those locations down there, an asteroid, Mars. But all of those, that's the next frontier. All of those are beyond low Earth orbit. So remember, 1 inch away from this globe, that's low Earth orbit. We're letting commercial companies do that now, right? We know how to do it. Let's let them develop that technology. Let's focus on trying to get to Mars. All of those destinations require high escape velocities that humans haven't really reached since Apollo 17. That was the last lunar mission. Long-term human exploration requires very large and heavy payloads, very large. And you'll see this is from 70 to 130 metric tons is the capability that we're developing with the Space Launch System. And I'll give you an idea of what that means. None of the existing rocket architectures that I showed previously come close to the required power to get to those velocities. Enters the Space Launch System. This is another picture of it. It is 322 feet tall. Very close to the size of the Saturn V rocket. It has a payload capacity of 70 metric tons. That's 15 elephants, full-size adult elephants. That's a lot of weight that you could take with that rocket to low Earth orbit. It has 8.4 million pounds of thrust. I'll give you an idea of how that compares to other vehicles. But basically, you've heard about the Orion vehicle. That Orion vehicle, if I can get the mouse, it's that part right here. That's the spacecraft. That's where the astronauts sit. And you've got a launch abort system in case something bad happens. They can get out of there and be safe. So that's the Orion up top. We're going to talk today about this rocket. What allows Orion to get out of the atmosphere? So you've got, I'm not going to give too many details, but you've got a liquid fuel core and solid fuel boosters on the side there. This is how it compares to the size of something you're more familiar with. The Statue of Liberty is 305 feet tall. The Space Launch System is 322 feet tall. There you have the Space Shuttle and Saturn V on the right. Now, when we're looking at thrust now, SLS is the most powerful rocket that has ever been built. Saturn V was 7.5 million pounds, 7.8, 8.4 million pounds now for a Space Launch System. So we keep pushing that envelope and getting better and better.
What do you mean by the term payload? That's over and above the rocket itself.
So the payload in this case right here is all of Orion. So it is the crew compartment. It's what's useful to us. So if it was a cargo vehicle like a satellite, the satellites, that's the payload. So it's everything, the important part of it. It's everything else.
Yeah,
Yeah, that's right.
baggage compartment.
There you go, baggage compartment. Yep. Thanks. We're not only developing one rocket, we're developing a family of rockets. There are right now 5 different configurations of the Space Launch System. That's I'm showing you the smallest one and the biggest one. We're starting here and we're moving towards that bigger one. That bigger one has a payload capacity of 130 metric tons. That's 25 elephants that you could take in your payload. That's a lot of weight. But that is what we need to get to these far destinations. To get to Mars, we need multiple of these to get that hardware on the surface of planets that are that far away. So designing, building, testing, and flying the largest rocket in the world takes exceptional work from thousands to come together. We have a lot of people working on this at NASA. With Space Station, that's our second most important focus right now. Launch vehicles are complex. They're a system of systems. It's not just a simple system. I'm showing you 6 different systems here, and all of these each have subsystems, and so it gets really complicated. I work in the structures environment system there, and I'm an aerodynamicist. I do wind tunnel testing and computational fluid dynamics. So I'm in that top right box there. So we have propulsion, we have avionics and software. That's the brains of the vehicle. That's the computer that allows it to keep pointing forward and getting to where we really need to go. We have the payload, which we just talked about. That's the precious part. That is the crew or the cargo, and that is what we're going to protect at all means. We have a launch abort system, which you've probably heard about. That protects the crew in case of an accident. And we have ground systems. We can't launch without a launch pad, without a tower that allows us to take the cargo up in the or the astronauts up in the crew module. Propellant storage. Obviously, we use a lot of propellant, so you have to store it before you load it up in the vehicle. All kinds of systems. Very complex. What is NASA Langley contributing to SLS? Well, when NASA Langley was founded, initially it was NACA, and it was that was in 1917. We're getting close to the 100-year anniversary of NASA Langley, by the way. That's what we started doing, was aerodynamics, wind tunnel testing, right? With the Wright brothers, Orville Wright was involved, and we're still doing that today. We're still doing wind tunnel testing. That's one of our fortes, is aerodynamics. So here you've got a picture of the NASA Langley 14 by 22. It's a low-speed wind tunnel. It's huge. It's the test section where we put the articles is about the size of this room. It's very large, and you can see it if you're driving on Commander Shepard Boulevard. This is a picture of one of the Space Launch System vehicles that we tested last summer. You can see, I'll give you a better picture right here. We tested the launch vehicle environments, the flow of the air around the vehicle. So right there you've got, this is a rendition, an artist rendition of the launch of the Space Launch System. On the right you've got an actual picture of our wind tunnel model. So you can see the similarities. Obviously it's scaled down. This model is about 6 feet tall, and it's made of aluminum. And what we're trying to do is measure wind forces on the vehicle, so that when it's sitting there on the launch pad, it doesn't start vibrating, or it's able to take the wind loads. So that we're going to start at the low speed, and we're going to go all the way to high speeds through some pictures here. This is some more pictures of the low-speed wind tunnel testing that we did on the liftoff configuration. And we do things like smoke flow visualization on the top right there. By introducing smoke in the flow, you've probably seen those types of pictures. We can see what the flow is doing and how it's impacting the vehicle. Some more pictures. We're now going through the speed of sound. This is called transonic testing. This is a very large wind tunnel called the NASA Langley Transonic Dynamics Tunnel. And this allows us to fly the vehicles at the speed of sound, at and around the speed of sounds, and really understand the aerodynamic forces there. It gets really complicated once you're trying to break that sound barrier. Back in the days of the Bell X-1, they had no clue what would happen when we're going to fly through that sound barrier, And that now we really understand that better, and it's mainly due to wind tunnel testing. And then we have supersonic testing. So as you're flying through the atmosphere, at some point the atmosphere is going to get really thin and you're going to enter space. Right around that point, we're going about 5 times the speed of sound. That's what's called supersonic flight. And so in this tunnel, that's the unitary plan wind tunnel, still here at Langley. We're currently testing in that tunnel. We can go to 5 times the speed of sound at a much smaller scale. It's a 4-foot by 4-foot test section, so this is a pretty small model. It's about 35 inches long. But we can get to those speeds, and then we can scale everything to full-scale flight, and we can figure out what the aerodynamic force is going to be. Some more pictures of some of the testing throughout the whole Mach range. And here's a flow visualization of supersonic flight. This is a launch vehicle that was designed 5 or 6 years ago, and we did a lot of research here at Langley on that vehicle. You can see some shock waves there. When you go past the speed of sound, you'll have some really, really high compression pressure waves that are going to form. And so the flow is coming left to right here on the vehicle, and you can see these shocks. With the naked eye, you cannot see it, so we use an instrument, a special instrument, to see that. But it gives you an idea of the really harsh environment that we're flying through. And so we do testing in the wind tunnels. In the wind tunnels, we let nature tell us what the answer is, right? We have a model. We measure forces, aerodynamic forces on the model, but we're letting the flow tell us what that force is. Well, with large computers today, we know what the equations are that describe the flow, so we can try to solve them numerically in a computer. And so that's what this is showing here. You've got the Space Launch System in the center here, and we're looking at variations of pressure on the vehicle, so variations of airflow velocities on the vehicle. And all around there, you've got different cuts along the vehicle, and this is liftoff configuration. So the flow is coming from the bottom. Let's take the bottom left picture there. The flow is coming from the bottom, and you can see the wake of the flow around the Space Launch System here. Wake flows are extremely hard to predict and understand from a fluid dynamics standpoint. In 2009, NASA Langley led this effort, which was a full-scale flight test of the Ares 1X rocket. These are actual pictures, they're not artist renditions, and we launched at Kennedy Space Center October 2009. You can see there, the left picture, you can see the air condensating around the vehicle because of those transonic shocks. Pretty cool picture. And you can see the amount of thrust there. That's a pretty big flame. Don't want to be nowhere near that. That was really an amazing feat, and really got us back into the business of developing rockets. And now we're getting pretty good at it. This is another contribution that's ongoing. This is going to be the first flight test of the full-scale Space Launch System in 2017. Look forward to it. It's going to be launching from Kennedy Space Center, and we're going back to the moon. This one won't have any astronauts because it's the first flight. We want to make sure everything works well before we put astronauts in it. But we are going back to the moon. So it's going to launch. It's going to go around an Earth orbit, and then it's going to fire some thrusters and go into a translunar injection orbit out around the moon and back to the Earth. That's going to be an exciting launch.
How long a trip?
It is several days. I don't know exactly, but I think it's around 3 days.
Sounds like it's like 2 hours.
Yeah, I know, yeah. Yeah, a couple hours is what it takes to get to the space station. To get to the moon, it takes several days. And then to get to Mars, it's several months. It's 6 months, 6 to 8 months. Okay, so back full circle around, back to history a little bit here with let's talk about the birthplace of U.S. manned spaceflight. In Hampton Roads, we had the NASA Langley Research Center, and this is where everything started. The Space Task Group in 1958 was started. It was a group of around 45 engineers, and they were all working here at NASA Langley. They were led by a person by the name of Robert Gilruth, who's now a pretty famous guy.
He died last year.
Yeah, he did, and he was tasked with managing America's manned spaceflight program, including Project Mercury. That was before Kennedy made his speech. So it started out pretty slow, but they knew what they needed to get going. So so let's see, from 1959 to 1962, the Mercury 7 all trained here at Langley. Those are the first 7 U.S. astronauts, and they're all there. And we're still lucky to still have John Glenn with us. But these were really pioneers. The risk that they took to get on those rockets there was huge back in that day. There's no doubt about it. It was a huge risk, and thanks to them, we are where we are today, and we can do things a lot more safely today. This is the Mercury capsule that was tested here at the Langley Full-Scale Wind Tunnel. It's you can see the scale of that vehicle with the man staying on the ladder there, and that tunnel has tested so many airplanes and so many spacecraft. So it was low-speed wind tunnel, but still, back in the day, that's what they did here at Langley. And in 1962, after President Kennedy's announcement of the Apollo program, with a goal to land on the moon by the end of the decade, the Manned Spacecraft Center was created in Houston. We needed a lot of land for that, so they went to Houston. It's now called the NASA Johnson Space Center. And all of the Space Task Group engineers from Langley moved to Houston, including these 3 people. I already mentioned Robert Gilruth. He was the first NASA Johnson director. We have Max Faget, who was the inventor of the space capsule, which we are still using today. You saw the Orion space capsule. It's kind of a cone shape with a heat shield. That was his idea. And he did a lot of that work here at Langley. And then we have Chris Kraft. Born in 1924. He was NASA's first flight director at the Houston NASA Johnson Space Center. And he was NASA Johnson's second director. You beat me to it. Oh, man. Chris Kraft, Christopher Columbus Kraft Jr., he was born in Phoebus, Virginia. It's not too far from here. Mission Control Center in Houston was renamed the Christopher C. Kraft Mission Control Center in his honor in 2011, and that's him accepting that honor down there at Houston. It's a pretty cool thing. He was the first flight director. So astronauts are pretty cool people, you know, and our nation has had, you know, several hundred astronauts. Flight directors, they're even more rare than astronauts. You don't mess around with flight directors. They're pretty cool. And this is a time capsule at the Air Power Park in Hampton on Mercury Boulevard that was interred in 1965, by the city of Hampton in honor of Chris Kraft, and it will be opened 100 years later in 2065. So I've already got that date on my calendar. Make sure I'm going to show up there. And good. Let's all go see that. It should be cool. So this pretty much, I'm towards the conclusion of my talk. With the Space Launch System, NASA Langley is again contributing to one of the agency's highest priorities right now today is to develop a deep space exploration capability that will land humans on Mars in the 2030s. So please, tell your friends and your neighbors that's what NASA's doing. We're going back to Mars, and we're going to get there in the 2030s. Hopefully early 2030s, so I can try to get on one of those spacecraft and walk on Mars. One thing to look forward to, that's happening this year in a couple months in December, and you may have heard about it from the other talks. That's Exploration Flight Test 1, December 4th, launch from Kennedy Space Center. We are carrying the Orion spacecraft with a different launch vehicle because the Space Launch System is not quite ready yet. And we're going around, on an orbit around the Earth, firing some more thrusters, getting even higher, and re-entering the atmosphere at 20,000 miles per hour, as if we were coming back from Mars or the Moon. So that's going to be a really cool thing. Don't miss it. You'll certainly hear about it on the news. Tell people to try to catch it, and hopefully we'll be successful. So this concludes my talk. Thank you so much for paying attention and asking questions. It'll be my pleasure to take more questions if you have any. So thanks again for your time. Yep.
Do you know of any reason other than political ones why that Space Center was moved to Houston?
I think they looked at a lot of places they had. Oh, I'm sorry. The question was, why did we move the manned Space Center to Houston, from Langley to Houston? Yeah. So okay, you may know the answer. Okay, all right. Okay, well there you go.
The question was worded, do you know of any reason why we moved to Houston other than political?
Oh, other than political. I don't know. Maybe the land, but you probably, your answer is probably as good as mine on that one. Yeah.
You were there when they happened.
I'm going to take that one over there.
Computer simulations today, why do you still need to use a wind tunnel?
Okay. Question is, we have computer simulations today. Why do we still need wind tunnels? Great question. If you ask that question in 100 years, maybe I'll be able to tell you we don't need wind tunnels anymore. Maybe. But the reality of things is that flows, the fluid dynamics of flows is so complex that even today, with the most powerful computers in the world, we are not able to do what we can do in a wind tunnel. And even though we're progressing really fast with technology and computers, it's a consensus, there's no debate about this, that we will not be able to do everything with computers for a long, long time. But today we use both of those we use computers a lot more than we did even 10 years ago. We use those two as very complementary tools. We learn things from the computer simulations, and we learn other things from the wind tunnel. So we could not do anything without both.
What contractors are building the various parts of the
So the core is Boeing. The core stage is Boeing, and that was the middle section of it. The boosters is ATK. They built the shuttle boosters. It's the same boosters except a bit longer. And the spacecraft, Orion, is Lockheed Martin.
Is there any international collaboration in this effort?
There is, and it's growing. We are working with the Europeans to potentially use this launch vehicle to launch one of their payloads, one of their spacecraft. They have a fairing that we're going to try to use on this spacecraft, on this launch vehicle, and launch it very soon. So there is some. We're trying to do the most we can here with our capabilities in the States, but at some point, international cooperation is very important. So, yeah. Yeah.
What is the mechanism for reading the data from the wind tunnels is one question, and the other is, wasn't one of the wind tunnels recently destroyed, and if so, why?
Okay. So I love that topic, or the two topics there, but the first one is what I do every day, so I can talk about it all day. But how do we gather data from the wind tunnel? We have, so when you step on a scale, that gives you your weight, and that's a one component scale. It gives you your weight and nothing else, right? We have what's called 6 component scales, and they're like a very small, what we call balance, a 6 component scale. And we mount those scales inside the wind tunnel models. I don't know if well, there we go. Inside that model, there is a 6 component scale, and when you blow wind on that model, that scale is measuring the forces in all directions, not just, gravity. It's measuring all of those aerodynamic forces, and therefore, out of that, we can know what the air is on the force of the air is on that vehicle. Second question is a complicated one because of the multiple constraints that we have. Recently, you may be thinking of full-scale tunnel, which is actually this one that was demolished several years ago, and some of those tunnels are old and funding is always an issue. These capabilities are really national assets, and we're trying hard to protect them. Like I said, we're going to need them for a long time, so we better take care of them. It just happens that some of them, we haven't been able to take care of them as well as we should, and so we had to demolish some of them. Thankfully, we've got capabilities in other places, but we're really at a point here where we don't have duplicate capabilities around the nation. So as soon as we start demolishing new facilities, we're going to have some problems.
About 7 or 8 years ago, one of the NASA engineers spoke of the technology that he was in charge of. He, I believe, applied the paint used on simple planes in the wind tunnel, and then they observed the stress changes of the paint itself. It tended to change color and patterns, showing the stress on the models. Is this technique still used in any of our space?
It is. It's called pressure-sensitive paint. We also have temperature-sensitive paint. It's called pressure-sensitive paint, and we also have a different paint. It's called temperature-sensitive paint, so we can see the temperature changes on the models. But you basically spray very carefully the paint over your entire model, and the reason you do it very carefully is because the cost of that paint, it's so hard to make. It's $4,000 for a 100 milliliter container. So you don't want to drip too much. There goes $100. But we spray carefully the paint on the models, and what we do is we shine it with a very intense lights, and we have cameras looking at it, and we can see the pressure of the air changing on it. And that's a technology that's really become mature in the last couple years. We're using it more and more, and we want to use it more. But that's at the forefront of measurements in the wind tunnel.
Can you say a little bit more about the benefit to society as a whole from this work?
Sure. And so the benefit. Oh yeah. The question is what if I can tell more about the benefits to society of the work we're doing here. So those are. It's a broad question, but it's a great one because and it's broad in many ways because the impacts are in multiple areas, but they're also very extended in time. Some of the technologies that we develop might have an immediate application in today's society. Some of them it might take 10 years, 20 years to find an application, and then it'll be revolutionary. So we're constantly pushing the envelope of what we can do just because of the extremely harsh constraints that we have to try to get into space. Temperature, harsh temperatures, pressures, and forces, they force us to build the best materials. They force us to really have the best instruments to measure those environments. And so you end up with technologies that, and many patents that end up being used or licensed by companies to develop, cell phones, technology in the cell phone, miniaturizing things. So for example, you saw that taking weight into space costs a lot of money. It's the heavier it is, the more costly it is. So we try to miniaturize things. We try to make them as small as possible, right? The space station has, can't remember how many laptops. It has 150 laptops, I think. But if those were desktops, that would be a lot more weight. So we have to miniaturize things because of that. And so in your cell phones, you have technology that comes from what we've developed over the past 20 years because of miniaturizing constraints. And then there's probably a lot of other things I could talk about. The medical field, of course. I mean, so we're doing research now on the space station and to try to understand how some biological processes act in the absence of a gravity force, right? We call it zero G. I'm always. It's not really zero G because really it's 1G. You're falling towards the Earth constantly. It's just that you don't have enough speed to get out of Earth orbit. So we're really always in 1G environments, but it's weightless. It feels weightless because you're falling, constantly falling. The moon is falling towards Earth all the time. It's just going at that perfect speed that it's staying in orbit. But when you're in zero G, you don't have the force of gravity. And so you can understand biological processes much better. And so health is another one, yeah.
How long before you're going to be able to use the SLS itself?
So first flight test is 2017. That's the first flight test without astronauts. We are looking at currently 2021 for the first astronauts to ride on SLS. We're hoping we can get something sooner, but again, that's all depending on funding. It doesn't take a lot more funding for us to be able to do great things, and you know as well as anyone else that when you spend $1 at NASA over the next 20 years, you're going to get much more than $1 back. So it's really depends on that, but basically, right now we're looking at 2021 for first. Yep. Let's go here first.
The ultimate future of the International Space Station.
I'm not sure. I don't want to give you a bad answer. I know that we are committed until 2020 to.
Jeremy, you want me to help with that?
Yeah, sure. That'd be great.
Am I on? So the space station was recently, we just recently made a policy decision to extend the life of the station to 2024. So now the United States is committed to maintaining it through that time. We think that it's probably got a limit somewhere in the late 2020s. We're trying to actually get the international community to help support it through 2024 at this point. The real long-term answer is that we think, and we're supporting U.S. industry to be able to replace the International Space Station with low Earth orbit stations. They won't look like the International Space Station, but they will provide a laboratory for scientific instrumentation. Some companies actually think their market will be tourism. So they're going to take people on a one-week trip to zero G so they can experience space themselves. So there's a number of different things. And then, of course, the government still needs to do research. So the government would buy, a ride and a slot to do an experiment. And so those are the kind of business models people are talking about. And there's billions of dollars of private money going into developing future low Earth orbit stations.
Great, thanks a lot. That was really helpful.
So many countries and companies are getting into thrust systems now, rocket systems. Could you give us in a descending order of capability
Okay, so the question is, commercial companies are developing technologies, engines, and rockets. In countries, yes. Although on the commercial stack of things, the U.S. is leading the way. These American companies who are developing these rockets are at the forefront of commercial rocket development. And so, are you asking the capabilities in order, maybe? Yeah. And so, mostly at this point, for commercial companies, it's all low Earth orbit capability. So it's that 1 inch away from the Earth,
Or suborbital.
And suborbital. Yeah. So suborbital, you're not achieving that velocity. So you're going to take off from one side of the planet, and you're not going fast enough, and you're going to re-enter at some other point. And so we've got Richard Branson, who's developing a suborbital Virgin Galactic suborbital spacecraft. You've got a company called Blue Origin. That is Jeff Bezos, who is the Amazon CEO. He's developing a capability for low Earth orbit. And you've got SpaceX. That's Elon Musk's company. He developed PayPal and those things. So it's the battle of the millionaires, who can get there first. So it's exciting. So I mean, of course, we've got launch capabilities in China, Russia, India, but those are mostly all completely government-run and funded. So I don't think, Europe has Ariane.
So I can add a little bit on
please.
that, because I just answered this question the other day in another place. So like Virgin Galactic, so first of all, everybody should know there are 3 U.S. companies that are building vehicles to take people, tourists, rich tourists. I think the cheapest ticket is $20,000. The most expensive is $2 million. So all these companies have different business models, and they've done analysis based on the number of millionaires that they think they can actually make money. They're investing tens to hundreds of millions of dollars. They're building spaceports and vehicles just like NASA did in the 60s. But their highest speed will be something like 2,500 miles an hour, because they're going to go up, they're going to get above the atmosphere, and they're going to have their tourists experience weightlessness for a matter of minutes while they go over this parabolic trajectory, and then they're going to come back and land. And so just compare that to, if you want to go to the moon, you need to be going 25,000 miles an hour. And if you recall, the energy equation goes as V cubed. So the power in these rockets that the commercial guys are developing is of the order of 100th of what we're developing at NASA now. It's a great development. It's very exciting that we've created this new industry. We have a new industry in the country that's going to make money and create jobs and so forth. But you got to keep in mind that the scale difference between doing a suborbital flight and doing a moonshot, and I think it's a great thing. It's one of the answers to your question earlier about what are the social benefits of what we do. Taken together over the last 50 years, investments in NASA have enabled the creation of this new industry, and in the end, it'll actually be a new market with many, many other companies besides just the vehicle. It's very similar to air transportation at the beginning of the last century. So space transportation I consider a market with vehicles as one industry and ground systems as another industry, and what you're doing up there, the payloads as another industry. So if you think about it that way, instead of in terms of just technologies, the payoff is huge. It's just longer term, and it's much harder to put. It's much harder for economists to actually calculate that value. Just to give you a hint, though, the airline industry today is a $150 billion industry. The airframe industry is also a $150 billion industry. And those are paying taxes back to the government. So in one sense, if you take a 70-year look, NASA is paid for many times over by what's been created out of NACA and NASA. So that's sort of answer to a couple of questions that are all related. If that's,
We have,
any more questions?
I think there's a question,
one?
yeah.
Yeah.
Are there any plans soon to send our astronauts on another spacecraft like the private ones
Yeah, that is,
to the space station rather than depend on Russia?
that is the plan. So the question was, is there a plan for commercial companies to take our U.S. astronauts to the space station? And that's exactly the plan. That is why we are letting those commercial companies develop those spacecraft so that we don't have to buy, $70 million tickets to space from Russia. So that is exactly what we're doing.
Do you anticipate having a time frame?
So I think the goal is 2017.
Yeah, so just last week, that's right,
Okay.
it's 2017, just last week, 2 contracts were awarded, one to Boeing and one to SpaceX. It was in the news. Those contracts were for those companies to build and certify as safe a human spacecraft that will ride on a commercial vehicle to the station. So the supply and the transportation to the space station will now be a commercial industry. Of course, most of their business is from the government right now. But that's why I mentioned earlier, is when the space station goes away, hopefully by then we'll have commercial stations that will provide this continuous market for these vehicle builders. Again, you start talking about it's a whole new market. It's not just a new industry. So that's 2017. Those
Yeah.
guys are on the hook to fly their vehicles by 2017 with NASA oversight and FAA oversight. By the way, the FAA is working with NASA to put in place the certification safety criteria that they have to meet, just like airplane manufacturers do. Yeah.
I said, what do they know?
Concerning all the new technology developed by NASA, what happens in the way of patents? Who gets them?
So
Does anybody, or is it free knowledge?
the patents, NASA does have a lot of patents, and we get patents for the technologies that we develop, but it's property of the government, so it's not, individuals will not benefit from those patents, but the government does. So the government can license those patents out and get some money back. I believe that's the case,
Yeah,
right?
we patent things, and then we make them available to anybody who will commercialize them. And the only reason we do licensing is so that somebody doesn't, we're very careful about the licensing because we don't want a company to come in and get an exclusive license and sit on it. So we're very careful about licensing just so that it gets broadly used.
Huh.
Otherwise, it's free. Yeah, and our inventors get a very tiny piece of royalties if something sells a lot of copies or something like that. You get a plaque,
Nice
mostly.
plaque, yeah. Yeah. So the question is, what components are reusable on the Space Launch System? And I'm going to say it's only the spacecraft. So only that Orion vehicle. We're planning on launching once a year, once every 2 years. Those are huge launches, expensive, and we're going to far distances. So it doesn't make sense to reuse. There's a curve that could describe at what point, if you fly so many times, does it make sense to try to reuse? Because reusable technology costs a lot, right? And so if we're only launching every year, it doesn't make sense to try to make that reusable. And that's for beyond low Earth orbit. For low Earth orbit, it does make a lot of sense because we're going to try to fly a lot more often. And so SpaceX, for example, is really trying the reusable thing. So they're trying to reuse as many of their stages as they can. And we did that for shuttle, right? We had reusable boosters, reusable orbiter. External tank was not reusable, but it is doable. It's expensive, so that's the trade-off. It's how many times you fly.
And NASA's using, the investments made in us to help them do that. Just saw a video yesterday of the launch from last week. I don't know if you saw that SpaceX launched another mission to the station. but we videoed the supersonic retro burn that they attempted, which was successful, to slow down their first stage to bring it down and land vertically. Now, it just dropped in the ocean for now, but they're learning one step at a time how to actually bring that entire first stage back to be reused. And that's the goal for SpaceX.
Man,
Unlike the other commercial launchers that are out there.
I want to see that video. I haven't seen it. That must be cool.
Tom Horvath.
Is it true that some of the components in the hardware for our vehicles can only be obtained from China or Japan?
I don't know. Do you know? I don't know if that's true.
I don't think so.
Yeah, I
Unless
doubt
there's
it.
something I don't know about.
Yeah. We can pretty much build anything, in-house or within the United States if it makes sense. So right now for Space Launch System, we're going to use engines. They're called RS-25s. Those were the same engines that the shuttle used. We already have a lot of those, so we're going to use those. We don't have to rebuild everything.
Your answer would include the computers?
Especially the computers. We have been prevented from buying hardware from China, like chips, because we found that they've embedded software in chips that they sell back to PC makers and so forth that can actually do bad things.
Yeah.
So we don't use any electronics from China.
And a computer on a rocket, the avionics bay, that is all completely custom made. It's not an off-the-shelf computer. It's every component is selected very carefully, and so
You had another question.
yeah.
If the life of the space station ends in 2024, what will happen to it? Is it just going to stay there? Will it be dismantled?
So if we do abandon it in 2024, what happens is it's only that 1 inch away from the Earth, and so the atmosphere is really, really thin, but you still have a little tiny bit of atmosphere, and it creates drag on the space station. And so what happens is slowly the space station loses altitude, and so if you don't push it back up, which is we do that very regularly, we push it back into its orbit, it'll just slowly come back and it'll burn in the atmosphere as it re-enters. So, it's a great question.
What is the cost to use the SpaceX vehicle to get to the International Space Station as compared to the $70 million Russian ticket?
Good question. Do you know that? And the question was the cost of SpaceX, riding on SpaceX instead of riding on the Russian vehicle. That is a tough question.
So the vehicle hasn't been fully developed, and so we don't know. SpaceX will tell you it's less today. Boeing has been in the business long enough that they don't even pretend that it'll be less. But until they actually prove they can actually build a safe vehicle, they won't know how much it costs. But it's a lot. It's a lot that we're paying the Russians. But so it's in the same order of magnitude, but we don't know if it'll be more or less.
But then again, it's nicer to be able to pay somebody in your own country that kind of money.
Exactly.
Exactly. It's U.S. jobs. That's right. It's U.S. jobs and U.S. technology development, and it's all part of our economic transactions in this country if we keep the money here.
Yeah.
So I'd just like to say, please come back next week. I already mentioned what the topic is. We'll be talking about EDL, human entry, descent, and landing at Mars. Very tough problem. And before I ask for your applause, I'd like to give a special thanks to Jeremy. He is in the middle. You saw that unitary plan wind tunnel test. He's leading that for Langley. He's in the middle of that, and they're working third shift. We try to save money, so we use energy when nobody else is using it. So we run that tunnel, which draws a lot of power, at night. And he's been working nights for 3 weeks while he put this together, and he did a great job.
It's almost time for bed. Thank you.
Thank you very much.
right.
See you next
Thanks.
week.
Thank you for doing